All right, so what we're going to do today is we're going to look at how to prove, using the epsilon-delta definition of limit, that the limit of a function going to a particular value is equal to a given limit value. Now, let's identify our definition of a limit first. So recall that in our definition of a limit, the general definition, we have x going to c. So in this case, c is -2. Our function is 3x plus 7. That's our f of x. And then L, capital L in our limit definition is 1. Now, recall that the definition of the epsilon delta definition of a limit says that if the absolute value of x minus c is less than delta, then the difference, the absolute value between f of x and the limit is less than epsilon. That's the general structure. So the important thing to kind of keep in mind here is that when we are dealing with an if-then statement of this sort, when we do the proof, we have to maintain this structure. So we have to start with x minus c is less than delta. And then we have to end with f of x minus L is less than epsilon. Now, the issue here is that if we go in this direction in order to construct the proof without doing any preliminary work, then we're going to run into problems because we're not going to be able to it's going to be more difficult to sort of make this transition. So what we do is we do the setup, we build up what we need to include in our analysis by essentially working backwards. This is a somewhat common technique for certain kinds of proofs. We work backwards from the then statement to come up with the relationship that we need with the if statement, but then we can't quit there. We then have to reconstruct the limit in the proof in the correct order in order to actually do the proof. So where we're going to start just with the work. Oops. Sorry, I killed my page break for my next question. Let's try again. So where we're going to start is we're going to do work. We're going to do some preliminary work in order to get the relationship that we need. And then we will move forward toward the final proof. So first things first, we're going to start with the then statement in our preliminary setup. And what we have to conclude here is that the 3x minus 7, 3x plus 7, sorry, minus 1 is less than epsilon. Now, if we simplify that, we get 3x plus 6 is less than epsilon. And then what we do is we factor out the 3, because in our statement here, we want x minus c, and there's no coefficient in front of the x. So we factor out the 3. Absolute value of 3x plus 2 less than There we go. And then we can pull the 3 outside the parentheses. And then move the 3 to the other side of the equation. Now, the thing that's important here is that in our problem, since we're going to x is -2, x minus a -2 is x plus 2. And so what we're going to do is we're going to set delta equal to epsilon over 3. That's the relationship that we need in order to do the proof going in the forward direction. All right, so now we're going to do the proof. Now, it's important to keep in mind, just because you found this relationship between epsilon and delta does not mean you're done. You are not done. You are like halfway through. It's like you're starting to build a house and you dug the foundation and then you quit. You still have to build the rest of the house. So the proof is the house. All right, so now what we're going to start with is our if-then construction. So suppose that the absolute value of x plus 2, since we're going to -2, that's our x minus c, is less than delta. And further, suppose that delta is equal to epsilon over 3. Then it follows that x plus 2 is less than epsilon over 3, and that we're going to now multiply both sides of the equation by 3. And basically at this point, we're just reconstructing this analysis that we did earlier, but in the reverse order. So now we bring our 3 inside the expression. And then we rewrite it in terms of our function, 3x plus 7 minus 1 is less than epsilon. And therefore, the limit as x goes to -2 of 3x plus 7 is equal to 1. We've satisfied the conditions. The limit of our function is equal to L whenever x is close enough to our c value, so less than delta, which is a small value. And then that implies that our function minus L is less than epsilon. And so what we've established is that we've started out with, this is our if statement. This is assumed we are within a small value of x plus 2. And if we relate delta to epsilon by this relationship, then we can prove that when we work out this algebra, we do get to f of x minus L is less than epsilon. So epsilon, again, is another small value. Now, again, the important thing about this proof is that you have to start with the if statement. You cannot start with then. That portion is simply sort of the work. And then the explanation of the proof seems somewhat opaque without this work, but that work is where that epsilon over 3 relationship comes from. But the proof itself requires that you start with the if statement and work through the algebra to establish the then statement. You can't do it in reverse. If this is true, it does not necessarily imply that the then statement is true. Now, if they're truly equal to each other, then sure, that equality we establish only at the end here. But once you're trying to do the proof, you have to start with if and then conclude with then. And that's part of the reason why this work is not itself the proof. Okay, so QED, which stands for quod erat demonstrandum, thus it has been shown. Our proof is done.